right? Yeah. She is visiting us from the Max Planck Institute for Astronomy in Germany. And she is visiting us for this week. So if you want to talk to her, you can find her at the former Johann Knaben's office in the first corridor. And she will be talking about new results on a molecular gas survey on M51. Is that right? Okay.
Thank you. Okay, so this is a complicated title for a very, very simple concept. And that is that the relation between star formation and the dense molecular material out of which it forms depends on the motion of that material. So I'll begin today by giving you an overview of the topic, an introduction to the survey that I've been analyzing to draw that conclusion. I'll show you how molecular gas is organized differently from galaxy to galaxy, and how the properties of the seeds of star formation, the giant molecular clouds, or GMCs, also depend on environment. And then I'll conclude by showing you how all of this wraps up together to give us this picture of how the dynamical environment of a cloud influences its star formation properties. So our gold standard for this relation between star formation and molecular gas is encoded in this plot here. This is the first spatially resolved measurements of both star formation rate surface density on the vertical axis and molecular gas surface density on the horizontal axis in a sample of 15 galaxies. Now, each point on this plot is from a 1 kiloparsec size region in this sample. And what you can see here is two things. First of all, the relation between these two quantities, star formation and molecular gas, is linear, very different from this sigma star formation to the 1.5 power of the molecular gas surface density, that is the Kennigan-Schmidt relation. So we have a linear relation, not a power law. And also, there's a universal gas depletion time traced out by all of these measurements. That gas depletion time is 2 gigayears. For reference, there's other lines of higher and lower gas depletion that are shown as dotted lines in this plot. Okay, that's really cool, right? So there's a direct relation between the star-forming material and star formation. But there is some scatter in this plot, both within galaxies and among them. And that scatter depends on the spatial scale being sampled. So now I'm looking at those same type of measurements in one galaxy, M51. So I've got the 1 kiloparsec size regions down at the bottom right, compared with increasing spatial resolution or smaller and smaller spatial scales as we move up in the plot. So as you go to 250 parsec sized regions, very high resolution, you see, in some sense, a very different relation between molecular gas and star formation. And the scatter now is booming. So I want to ask, what is the source of that scatter? Can we relate it to something physical? I also want to ask whether or not we can explain a real bimodality in star formation. I just want to put this plot up for those of you who are familiar with it already, not go into too much detail. But the difference that we see between star-forming systems at locally, so at redshift 0 and redshift 2, is about the order of that scatter that we see on the smaller spatial scales. And this has been interpreted as a true bimodality in star formation, or the difference between what some people call the main sequence of star formation and starbursts, which have an enhanced star formation rate per unit stellar mass and also per unit gas mass. So, but again, I'm most interested in exploring that scatter. That was the increase in the scatter as we went from large spatial scales to smaller spatial scales. Now, the two leading candidates for the sources of that scatter are either stellar feedback, so that is, the star formation event destroying its own birth cloud, radiation pressure and stellar winds changing the morphology of the gas relative to the stars, right? That's what I mean by stellar feedback. Or the second one would be evolution in the properties of the seeds of star formation themselves, based on how they form and how they evolve. So I'll mostly be taking this forward direction, and towards that forward direction, I'll be adding this perspective that is coming from gas kinematics and spiral potentials. So I'll be considering shear, shocks, and streaming motions in a little bit. Now, my study of molecular clouds, so measurements on the scales of molecular clouds, is building off of, yeah, John. Sure.
And you also have molecular clouds. Now, the star formation the star formation, once it's occurred, is not occurring in a molecular cloud anymore. Exactly how was the data, were the data in the first graphs made in such a way that you can compare the surface density of one with the other?
That's absolutely the point, is that you have this genuine offset between star formation and the molecular gas. And that star formation is not necessarily even related to the molecular gas that's just sitting next to it. So that's part of the source of the scatter. That's right. That's something, right? And then also when you look in spiral galaxies, there's an intrinsic spatial offset based on the way that gas responds to the potential. Absolutely right. Yeah. So that's something else to consider when you think about where the scatter's coming from. Thanks, John. Okay, so I'll be studying molecular clouds in a galaxy M51, but I'll be building off of results from a whole series of surveys of molecular clouds. In the last 5 years, we've seen a boom in this sort of work, basically because of instruments like the PdBI and the KARMA millimeter wave interferometers that give us high spatial resolution and sensitivity so that we can start to observe things on the scale of these individual GMCs. And this has been great because now we can finally start to understand GMCs in star-forming galaxies. Before this, about 5 years ago, we were still only limited to galaxies in the local group that are lower mass. Oftentimes, the molecular content is suppressed relative to the atomic content, right? And these just aren't the star formers that we think of as forming the majority of stars in the universe. And this is great. This has been a real big boost for understanding GMCs and their evolution. But typically, these surveys are limited to tens to hundreds of GMCs that come from particular parts of a galaxy, the interarm, the spiral arm, right? Now, these surveys give us this idea that a GMC is a GMC is a GMC. So GMCs are universal. Doesn't matter where it's sitting, arm, interarm, low mass galaxy, L-star galaxy, all of those GMCs have exactly the same property, and so they should form their stars in the same way. And in fact, it's the universality of the GMC that sort of seemed to be vindicated by this measurement of a universal gas depletion time, right? So to this body of work, I'm adding results from the PAWS survey. This is the PdBI Arcsecond Whirlpool Survey of CO1 to 0 emission in the central 9 kiloparsecs of M51. This is a combination of interferometric and single dish data. So we have resolution on the scale of 40 parseconds, so the 40 parsecs, so the typical size of a GMC in the Milky Way. And we have sensitivity to clouds above 10 to the 5 solar masses. Now, this is really unique because it gives us a wide field of view to sample a variety of environments for GMCs at the same time as a large number of GMCs to perform reliable statistics. So this was our view of M51 5 years ago. So this is about the resolution for those first spatially resolved measurements from Heracles and things. And this is our view of M51 today. So this is the integrated CO1 to 0 line emission across that central 9 kiloparsecs. And we can see that the gas has a very different distribution than we would have thought previously. In the interarm, we can see lots of fluffy, discrete structures, and the arm itself is not a smooth and continuous arm, but also knotty and clumpy. Now, we also have a really nice map of the kinematics of the molecular gas in M51. So for reference, this is what the line of sight velocity field for a galaxy in perfect circular motion projected at the orientation of M51 would look like. And then, of course, this is our line of sight velocity that we observe. And you can see that there are large discrepancies from that perfect circular motion case. In fact, we've got all of these strong non-circular streaming motions in the arm. I pointed out with arrows here and here. And we also see the influence of a nuclear stellar bar, but just focus mostly on all of these differences that we see along the arm. Now that's tracing these three characteristics of gas kinematics and spiral potentials: shocks, shear, and non-circular motions. Now I'm going to briefly give you an overview of how these three kinematic characteristics can influence the star formation properties of the molecular gas. So number one, shocks. What they tend to do is build very high gas surface densities, triggering star formation, right? But shocks can also enhance turbulence, so they can stabilize clouds. Then we have shear, which also stabilizes and potentially destroys clouds in the presence of differential rotation. So that is, you just have a clump of gas and you shear it out, right? Now, star formation should be favored in regions of low shear, and spiral arms are one such region of low shear, so keep that in mind. And then there's non-circular streaming motions, which by the end of the talk, I'll show you that they influence the coupling of clouds to their environment, so the dependence of the cloud and its properties on its surroundings. So the question is, which of these processes is dominating the stability of individual clouds? Well, that's what I'll be asking. But first, let me show you one very clear way that the spiral arm and kinematics in the spiral potential well affect the organization of molecular gas. And that's by comparing M51 and its molecular gas distribution to that in two lower mass galaxies, the LMC and M33, that don't have a strong spiral pattern. Now, I'm showing you here this comparison in the fairest way possible. That's with the same spatial resolution, the same velocity resolution, and shown here with the same intensity scaling. And there's not a problem with the projector, right? This is really telling you that the molecular gas in M51 is booming compared to these lower mass galaxies. Now, surprisingly, this difference translates into a difference in the properties of the molecular clouds. So GMCs and M51's arms are brighter and have higher line widths than the clouds in either the LMC or M33. And the spiral arm clouds are very different than the interarm clouds, which are more like the clouds in the lower mass systems. Now, we've done a decomposition of the emission to compare cloud for cloud between these. And what this allows us to do is make a cumulative mass spectrum, which I'm showing here on the right. So let me just step you through here. Basically, what we can see by looking at differences in the shapes of the mass spectra between these three galaxies, we can see differences in the formation mechanism behind the GMCs. So if I look, for example, at M51 arms, which are blue, compared to its interarms, which are in white, compared again to the LMC and M33 in green here, what I can see is that there are much more massive clouds that can be built up in M51 spiral arms than in either of the two lower mass galaxies. So what we see is that agglomeration of clouds in the spiral arms builds more massive clouds than you could create in any other system. Now, once you build these large clouds, they become gravitationally unstable. You can form a higher number density of clouds in line with Jean's instabilities. So that's what I'm showing here on the left. This is within M51 now, and each of these different colors represents a different dynamical environment. So the interarm clouds are the spectra that have the lowest number density, and then basically you stack up till you get to the spiral arms, which have the highest number density. And that difference in offset, in vertical offset there, is genuine, and that is tracking the fact that you have this high density reservoir that becomes Jean's unstable and makes more clouds. Okay. So this difference in cloud formation mechanism translates into difference in the star formation properties. So here are star formation tracers in the three galaxies, and you can see that things are different to 0th order. But I want to focus more on M51 itself and about the fact that it can build very massive clouds in the spiral arm. What that means is that we get preferentially massive star formation in the spiral arm. So that's being traced here in the FUV. So all of the green and blue are these zones of massive star formation in clusters that dot along the spiral arm, just like we expect, because we've been able to form these very massive clouds. Except it's not that simple. We almost have a complete picture, but there's one ingredient missing. And I think that can explain this. So in these two ellipses, there's a deficit of star formation. This is surprising because otherwise the molecular gas surface density is very high, and we would have expected lots of star formation if there is this universal gas depletion time, right? So let me show you again here. This is the CO1 to 0 map. Let's go back again to the FUV. Ooh. Where's that star formation? Well, it's also very obvious that there's a lack of star formation if you look at 70 microns tracing the obscured star formation. So there's a general lack of star formation in this zone where we would have expected lots and lots of star formation. Now what this translates into is a non-monotonic radial dependence for the gas depletion time. So that's molecular surface density divided by that star formation rate. which here in this case I've measured with a combination of H alpha and 24 microns. So you can see that there's lots of variation in the gas depletion time, and in particular, almost nowhere does it meet up with that universal depletion time that was measured in a sample of local spirals. So what's going on? Well, I think the thing to do is to ask what is shutting off star formation, right? So I've considered a few things, mostly related to those three kinematic characteristics of motion of gas in a spiral potential. So I can tell you what it's not from. It's not from shear. Okay, so here I've got a profile of shear in blue, and I'm comparing it directly with that gas depletion time again. Now, if shear, that is the destruction of clouds, were the source of these very long depletion times or very inefficient star formation, then every bump and wiggle in the shear profile would correspond with a bump or wiggle in the molecular gas depletion time. And in some regions it does, especially at a large galactocentric radius. You can see that there's an almost one-to-one correlation between the bumps and wiggles. Fine. But it's in between this zone that's highlighted by the vertical yellow lines that correspond to those two ellipses. The shear is almost zero. So we would have expected star formation in that zone. Those clouds aren't being destroyed in the presence of shear. Okay, it doesn't seem to be because those clouds along that portion of the arm have enhanced turbulence or turbulent support, right? I don't have a profile of that here, but I'll tell you that if I were to make a map of the velocity dispersion tracing the turbulent support of the clouds, then it has very little radial dependence. And also, clearly, support is not coming from stellar feedback, which would, of course, enhance turbulent motions. Because remember, that zone had little star formation in it. There was nothing in H alpha, 24 micron, 70 micron, right? So it's not star formation feedback. Okay, so what else can we say about clouds in that zone? Well, here I have a little plot showing you the stabilization of clouds in M51. So this is log of alpha, the so-called virial parameter, as a function of the luminous mass of clouds in our catalog of M51's GMCs. So alpha measures the balance between the kinetic support of a cloud and its own gravitational potential, right? So its mass. And for clouds that were perfectly virialized, we would expect alpha to fall between the two red lines there. You can see that only a few clouds are stable or virialized by this definition, 25% in fact. All these other clouds seem not to be virialized, which implies that there's some extra support, right? So, in fact, one of the candidates for interpreting very large alpha is pressure confinement, right? Because it looks like they've got more kinetic energy than potential energy, so you need something to sort of cap that off, right? And in fact, it looks like when we make a profile of molecular gas surface densities in the clouds compared with the arms, that the ambient medium of the cloud is in fact supplying that pressure. So now these are surface density profiles. So clouds, individual measurements for the individual clouds are shown in gray, and then I've got the surface density in the arm. And I'm using the surface density here as a proxy for the pressure. So you can see that in some places, the pressure exerted by the arm exceeds the pressure of the cloud itself, implying again that there's a lot of pressure coming from the environment. So external pressure helping to keep clouds stable. But so in M51, we've only considered the molecular gas because the molecular gas surface density is 10 times higher than the atomic. The M51's ISM is very well known to be molecule dominated. That's right, yeah. Okay, so this holds on at the global level in M51, as in a whole bunch of other galaxies, including the LMC and M33, those two galaxies we considered a few slides ago. So now I'm plotting the internal pressure on the vertical axis against the external pressure that we calculate just based on the weight of the ISM in the presence of the stellar disk, right? And what we can see is that, yes, okay, the internal pressure is maybe a little bit higher than the external pressure, but these two pressures track along with each other. So somehow, the GMC inherits its internal pressure from its environment. But more importantly, in our case today, is the fact that the two are very similar. So there's a near balance between the internal and external pressure. The external pressure is clearly playing an important role in stabilizing the clouds in M51. So in this case, I'm going to be very concerned about what that particular balance is. Because if I've got comparable internal and external pressures on the clouds, if I perturb the surface pressure of the cloud, then I can make the difference between stability and collapse. Now, what I'm going to consider here is the influence of gas motions on that surface pressure of the cloud. Now, to do that, I want to look at how the gas is moving. So the first way that I've gone about that is I've calculated the map of the present-day torques exerted by the bar and the spiral on the gas. So to do that, I've taken a nice stellar mass surface density map of M51. I've converted that into a potential, and then I've calculated the gradient of the potential to tell me what the torques are in the presence of this non-axisymmetric structure. So that looks like this here across the PAWS field of view. So this is my torque map, and all of the regions that are white are marking regions of positive torque, which drive radial gas motions outward. And all of the places that are black correspond to negative torque, which drives radially inward gas motions. Overlaid on top of that are contours of the CO emission. Now, what I can do with a torque map like that is make a torque profile like this down here. Again, the color coding is the same. Black is negative torque, white is positive torque. Right? And now, we've been interpreting plots like this for a while now, and what they tell us is that there are a series of distinct dynamical environments in M51. And lucky for us, all of those dynamical environments correspond very, very well with the dynamical environments we know to be there from independent measures, pattern speed measurement, just the morphology of the structure itself. So we can see a zone dominated by the nuclear bar. We can see the zone of the spiral arm, or we can see a transition to a material pattern at large radii. But I don't want to talk about that today. That's a whole nother talk. What I want to show you now is a comparison between the torque profile and that molecular gas depletion time. So everywhere except for the large galactocentric radius where we saw that shear was responsible for the variation in the gas depletion time, you can see at smaller radii there's an almost inverse correlation between the torques and the gas depletion time. So negative torques disfavor, according to this, massive star formation. Okay. So the reason why, right, so just to let you know, right, the solid gas seems to be forming stars like it should, whereas the gas that's in motion is prevented from forming stars. And my explanation for that is with dynamical pressure. So let me just graphically try to illustrate what I think is going on. So this is the Bernoulli principle. So basically what happens is that when I take a cloud and I then put it in motion in the spiral arm potential, then all of a sudden I reduce the pressure of that gas. That reduces the surface pressure on the cloud, which then increases the stable mass for the cloud. So that means that a cloud can be more massive and not collapse and not collapse. Right? Now this increase in the stable mass means that there are fewer collapse unstable clouds per freefall time. And so this all translates into a variation in the star formation efficiency. Or in the presence of streaming motions in particular, we have a reduced star formation efficiency. So let me show you with an expression what that looks like. So this is just an energy balance between gas in the interarm and in the arm. And what I get is that there's this nice relation between the natural log of the gas depletion time and the streaming motion squared, right? So let me just skip that for now and show you what this looks like graphically. So now I'm plotting these two boxed quantities on this plot here. The different color coding represents different dynamical zones that we identified based on the torque profile. But let me just show that the dotted line here is this magnitude of the streaming motions throughout each environment. And then the straight, nice solid line is this same gas depletion time I'd shown you before. Now the two track each other, right? You can see that all of the bumps and wiggles in one are in the bumps and wiggles of the other. So what does this look like when I plot one against the other? That's what I've got here on the right-hand side. So now I'm just taking those two curves, taking points from throughout those curves, and plotting them in a scatter plot one against the other. And I'm going to build this up as a function of dynamical environment. So from the inner radius to the outer. And what you can see is that there's a very good correlation between the two quantities, just where we expect them. Now, according to this expression at the top, the slope of each of these linear relations tells me something about the slope of the mass spectrum of the GMC. Don't worry about that too much. The intercept with the vertical axis tells me about a fiducial gas depletion time. And both of these quantities agree fairly well with what we know from direct measurements of the cloud mass spectrum, for one, and then this gas depletion time that we measure on average in galaxies. But there's a real difference between the intercept and the average gas depletion time. Sorry, this is not coming out too clearly, I think. But to explain really the implications here of this dynamical pressure, let's go back to the Kenniket-Schmidt plot. So this is star formation rate, surface density, again on the vertical axis, molecular gas surface density. And each of these points now corresponds to one of those regions that I showed you on the previous plot. And the size of the point scales with the magnitude of the streaming motion. The yellow points here come from those yellow ellipses. And so what you can see here is that preferentially galaxy regions with the highest streaming motions are sitting at the longest gas depletion times. When the streaming motions are small or negligible, then you're forming stars more efficiently with a shorter gas depletion time. So streaming motions lengthen the gas depletion time. So let me show you how these measurements compare with starbursts. Now, these are starbursts from the Kenniket 98 sample, and I just want to make the distinction here. These are not star-forming galaxies, they're star-forming regions. So these regions are typically coincident with resonances, and so by definition, you're building up a very high molecular gas surface density in the absence of streaming motions. At these resonances, the streaming motions are zero, all of the gas is sitting around that's not flowing anywhere, and so you're able to build up high star formation rates. So, not surprisingly, all the points in M51 that come from the regions of low streaming motion sit in very good agreement with the starbursts. And it's only those points that have the long streaming motions that sit at much longer gas depletion times. So how does this compare with other normal galaxies, normal spiral galaxies? Well, now I've added these points, and they're grayscale color-coded by morphology. And what you can see is that some of the earlier type galaxies are sitting at long depletion times. When I step out in morphological type to later galaxies, lower mass systems, the depletion time starts to shorten once again. Let me show you that in a little bit more detail. So here is the plot of the molecular gas depletion time as a function of morphological type from the work of Adam Leroy. It's submitted now. And what we can see is that, as expected, the depletion time is longer in early type massive disks, longer than in the lower mass later type disks. And that's because, to first order, the streaming motions are higher in more massive disks. So, more massive disks, which become unstable to spiral structure, drive stronger streaming motions. The stronger the streaming motion, the longer the gas depletion time. So we can explain this decreasing trend with morphological type based on this dynamical pressure. So let me just repeat that again. So the early type spirals have the longest gas depletion times because in those systems the streaming motions are longest. In lower mass dwarf galaxies and in starbursts, the gas depletion time is much shorter. Now, in the dwarfs, in this case, it's because those galaxies are so low mass that they never become unstable to bar and spiral structure that drives the streaming motions that lengthens the depletion time. Now, you make a first stab at relating star formation at all times with this expression for the gas depletion time. And to do that, really, I think it's best to write things in terms of the Toomre stability parameter Q and the gas fraction of the system. So that's what I've shown you here. And what you can see here is that the higher the gas fraction, the shorter the gas depletion time. Right. And so again, basically having a higher gas fraction reduces the impact of dynamical pressure. Because now the stellar disk in relation to the gas disk is much, much smaller. And so you're not driving streaming motions relative to, say, the turbulence support of the gas as strongly. So just graphically, let's go back to this plot from Dadi et al. We can see that, or my interpretation of this plot, is that all of the systems that have high gas fraction, i.e. systems at higher redshift, where the gas fraction is intrinsically higher, have the much shorter depletion times. And it's only when you step down in gas fraction that you start sitting near the sample of local galaxies that are shown in the color contours with the longest gas depletion times. And so in my picture, the normal spiral galaxies aren't normal. It's the starbursts that are forming their stars very quickly in 1 gigayear that are forming their stars like they should be. But in the presence of non-circular motions, you get a lengthening of the depletion time. And I just wanted to note, too, that this picture of gas fraction, or the influence of the gas fraction, can also explain the fact that Milky Way cloud points, shown in red here, also sit at high depletion time, because there we know that the gas fraction is, 99.999%. Right? So now we can relate systems at all stages, at high redshift, low redshift, locally, in star-forming disk galaxies. So, in summary, do extragalactic GMCs have uniform physical properties? No. My way of showing that was this increase in mass, although there's also increases in brightness, temperature, and line width for M51's GMCs compared to local dwarf galaxies. Does the dynamical environment matter? Yes. We saw that very clear link between gas depletion time and the torques, identifying different dynamical environments. And then the way that we interpreted that was that gas flows impact cloud equilibrium. So, thank you.
Yeah, thank you very much for this nice talk. And now we have time for some questions.
I have a comment. We're working now on systems which allow us to vary the dynamical interaction parameters, namely interacting galaxies. And we are finding clear differences between the molecular clouds and the H2 regions, between the physical parameters in regions which have obviously been affected by dynamical interaction and regions which haven't. That's just a comment which seems to fit globally with what you say.
Right. Great.
I got it completely wrong, but does this picture fit within the cold flow scenario, high redshift, when you got lots of gas coming in? There's a lot of angular momentum there. When you're telling me is that you should have delayed star formation, but
right. So that's why the gas fraction is important, because it's very clear that a lot of these starbursts, systems at higher redshifts, are associated with very large streaming motions. Fine, that's right. But so I glossed over it, but it's really the streaming motions relative to, say, the kinetics of the gas, the turbulence in the gas. And I think in those cases, we know V over sigma is lower at earlier times. The disks are puffier. And so that even though you're driving all of these very strong streaming motions, relative to just the turbulence in the gas, dynamical pressure is less important. So the higher the gas fraction, you sort of start turning off dynamical pressure again. And you can really only see it when you decrease the gas fraction and then start making disks that are driving again once again strong streaming motions. That's a great question. Yeah.
You mentioned early type spirals and then small galaxies, but you didn't mention late type spirals. And in late type spirals, the streaming motions are just as strong, if not stronger, than in early type spirals. Therefore, I infer that you would be saying that it's the ratio of those streaming motions to the turbulence that's different, because late type spirals have just as strong streaming motions, if not stronger, than early type spirals, but they are much more rapid star formers. So what do you say?
Well, so yeah, I mean, there's always this normalization by the turbulence, but I was not aware of any nice correlation of streaming motions with morphological type, right? My interpretation is based on that first order
What I'm saying is that the streaming motions in late type galaxies are at least as strong as those in early type.
As a function of stellar mass. Whereas this, I don't mean to.
The velocities that you measure, the amplitudes.
Well, they're all typically 10 to 15 kilometers per second, right? But I think that I don't know what to reference there. I don't know if there's been a study that shows conclusively that the streaming motions are independent of morphological type. And in fact, my interpretation was that I expected streaming motions to be higher in the earlier type spirals.
Well, it's difficult to quantify, but our work on resonances shows that streaming motions of the normal type, tens of kilometers per second, are at least as persistent in late type galaxies as in early ones. That doesn't mean I'm not quantifying it very much.
Right, and that's what I'm talking about. Not necessarily the presence of. There can be plenty of streaming motions in the later type disks. I mean the magnitude, and I suspect that the magnitude is changing as a function of.
Do you have evidence? Do you have evidence for that?
Well, I'll tell you what. I was able to, with the same expression that tells me that the streaming motions are related to the mass of the galaxy, I was able to reproduce the observed dependence of the pitch angle of the spiral on the Hubble type. So you get both of those two things for free. So, we've known for years that, spiral arm pitch angle is one of the things that people first used to classify galaxies, right? The later type spirals are more open spirals than in the earlier type disks, which are tighter. At the same time as you get tighter spirals, you also get stronger streaming motions. So I still think that the fact that we see the tighter or this morphological dependence of the shape of the spiral, we also get stronger streaming.
We may be able to give you the observer's answer to that. May be able to do so.
That would be great.
Any more questions? Okay, then let's thank our speaker again and have a good day. Bye.